All right, let's analyze the basics of friction here, okay? And what I've drawn for you are a couple of situations you're gonna run into in several problems. But I don't want you to get too caught up in any one specific thing, but more generally look at the bigger idea behind how to account for friction when we're dealing with forces. So I put a formula up here, and this little Greek letter mu, it represents what we call the coefficient of friction. Coefficient of friction. And this is a number, like a decimal right here, that basically describes when two surfaces are in contact with each other and there's a certain type of motion between them, it describes for us the effect that friction has. Okay, I don't want to get too much more on this video into the math behind it, but I just want you to know that it's a decimal that basically kind of in a sense describes how much friction there is. Okay, and the way it's calculated is we take the force of friction that acts on that object and divide it by the normal force on that object. We need to go analyze what those mean so you understand where it comes from. Now over here I just rearranged it because a lot of times we're trying to figure out how much friction there is, and the way we figure that out is we look up the coefficient of friction for that situation and we multiply it by the normal force. So all I did was multiply the normal force over to this side to rearrange it to get that equation. But what I did is I picked a situation here that's horizontal, okay, so we don't have any angles to worry about. I grabbed a very easy mass of 10 kilograms just to show you how to approach this, okay? So basically we're going to take a situation like this. Let's say this box is sitting on a floor, all right? And the coefficient of friction between the box and the floor as they one slides against the other is 0.62. I just made that number up. That's something that's going to change with each situation we're given. Let's analyze the forces that are going on. So let's say this box is just sitting there. Now when it's just sitting there, we're going to have the force of weight pulling it down towards the ground. Okay, gravity is going to be affecting this. So the way we find that out is we do the mass times the acceleration due to gravity. So in this case it's going to be 10 kilograms times 9.8 meters per second squared, which is going to give us 98 newtons. So we have 98 newtons pulling it down. Now this box, if it's not actually falling through the floor or rising up off the floor, if it's just sitting on the floor, then that means there must be a force that the floor is pushing, according to Newton's third law, an equal and opposite force that's pushing it away from the ground. Okay, something that's supporting it. That's what we call the normal force. The normal force is the supporting force typically, where if something is on a surface, it's the thing that's essentially resisting gravity. So the normal force would be pushing up, and in this case they would be the same. The normal force in this case is also going to be 98 newtons. Now you could easily describe this one as positive and that one as negative. Like there's a lot of ways to write this. But conceptually, we got 98 newtons pushing up from the floor and we got 98 newtons pulling down from gravity. Okay, and those two things cancel each other out and the box sits there at the same level without sinking and without rising. Now over here, that's not true. If a box is sitting on a ramp, a lot of times it's going to start sliding down. So all of a sudden over here, we would not have that exact same scenario. But let's take a look just at this one to begin with. Okay, now, if I were to actually have, say, a rope or something, and it starts pulling this box to the right, okay, I'm going to have an applied force big enough to overcome friction. What you need to understand about friction is it always opposes motion. So if I have an applied force moving it this direction, then friction is always acting in the opposite direction. So you have to start by understanding which way is this moving, and friction is always going the opposite way. It's always impeding that progress. So I would have a frictional force acting in this direction. The two of those would be acting in opposite directions. If I were going to put signs with it, I would call this a positive force and that probably a negative force. But like I said before, there's a lot of ways to set this up conceptually. I just want you to understand what it means. If I want to know how much frictional force is acting on this object, it's related to the normal force, that surface that's pushing up on it. Okay. Here's my formula I'm going to use. The force of friction is going to be equal to mu times the normal. So if I want to find the force of friction in this case, I'm going to take a mu of 0.62, which is just a unitless ratio, it's like 62%, times the normal force, which happens to be 98 newtons. Okay. So I'm going to grab a calculator and just type that in. It's like giving me a percentage of 98 98 times 0.62, and I get 60.76 newtons. So my frictional force is 60.76 newtons. So there's 60.76 newtons of force holding this thing back. That means my applied force is going to have to be at least 60.76 newtons. Like if I apply the exact same amount of force to this as I do to this, I might be able to get this thing just to barely start moving at a constant speed, but I couldn't accelerate it. In order to accelerate it, or to keep it, let's see, to speed it up, I'm going to have an applied force that's bigger than the friction. If I have an applied force smaller than the friction, this isn't going anywhere. And if my applied force is exactly equal to the friction, then I may be able to keep it moving at a constant rate without speeding it up or slowing down and maintain a speed, but I can't actually speed it up. And that's how we're going to account for friction. It's always going to go in the opposite direction. Now I have this other one drawn over here just to kind of point you in the right direction. We'll be getting into a lot of this in class. But the difference here on an angle is that gravity is still pulling things down directly towards the ground. Okay, so my force of weight looks like this. But my normal force is actually the surface that's pushing against it and supporting it is pointing out at an angle. The normal force is perpendicular to the surface that it's touching. So you see those two things don't exactly go opposite directions of each other like they do on a flat surface or horizontal. So we're going to have to use some trig in this to figure out exactly how much force is pushing against it. It's not equal to the weight. It happens to be a little less than the weight, but it's a component of the weight where we're going to use trigonometry to find that out. And it's going to look a lot like the components you used in projectiles and other things. So this is a slightly different situation. And then if this was sliding down the ramp, friction would be holding it back. If I was pulling it up the ramp, then friction is impeding that, so it would be pointing down the ramp. So we have to just kind of adjust the situation to fit whatever we're analyzing. But this is your general formula to be able to analyze a frictional force, and you got to remember that the frictional force is always going opposite of the direction of motion.